You are listening to The Vocal Technologist. Spoken tech for your ears.
So the bit rattling around my head is this. We are obsessing over how smart AI models are getting. But the truth is, the real bottleneck is just how fast they can spit out tokens.
Yeah, I mean, it is the quiet reality of the entire industry right now, honestly.
Right.
We have hit this hard physical limit. Chasing pure, omniscient intelligence is, well, it's taking a backseat to sheer, unadulterated speed.
Welcome to Vocal Technologist, where we pick apart the tech updates actually worth your time. And you are spot on. It really feels like the whole DevOps and AI space has collectively pivoted.
Oh, absolutely.
It's no longer about building the ultimate super brain that can solve the universe.
Oh, no, it's not.
It is entirely about how fast we can get a good enough answer through the pipes without, melting the server racks.
Yeah, exactly.
We are seeing this brutal obsession with infrastructure scaling and efficiency, and we need to untangle what that actually means for the code we write and the systems we manage.
Because if you look at the telemetry, we have crossed a really fascinating threshold. Yeah, the models themselves are, for most intents and purposes, they're smart enough for everyday coding and research tasks.
Okay, sure.
The math actually shows that once a model can output roughly 100 to 200 tokens per second, that feels instantaneous enough for interactive work with a human.
Right, because if I'm sitting at my desk watching code generate, I can only read and comprehend it so fast anyway.
Exactly. You are the bottleneck.
Right, like if it spits out 5,000 tokens a second, it doesn't actually make me any more productive. I am still the slow meatbag in the chair.
That is the exact problem we are facing. Any further acceleration of the model itself, it just starts hitting severe diminishing returns.
Because we just can't keep up.
Exactly. The core model is no longer the slow part of the chain.
So what is?
The real bottlenecks are the tool calls, querying your external databases, waiting on your local hardware limits, and human review.
Oh, wow.
So the engineering competition, it's no longer just on some leaderboard for logic puzzles. It is entirely shifted toward serving speed and slashing overhead costs.
Which brings us to the part nobody is really talking about.
Yeah.
The sheer length companies are going to just to shave off milliseconds and megabytes. Like I was looking at how Cloudflare is handling this at scale.
Oh, their approach is wild.
It's crazy. They are hosting these massive models like Moonshot's Kimi K2 and GLM, and they are essentially starving them.
Yeah.
They're putting these models on a severe digital diet.
A very aggressive diet. Cloudflare is leaning heavily into techniques like quantization to compress the model weights.
Right, to shrink the file sizes.
Exactly.
Yeah.
For a model like GLM, they are taking it from 8-bit integers down to 4-bit integers.
Wow.
So by chopping the mathematical precision in half, they shrink the entire checkpoint from 705 gigabytes down to 421 gigabytes.
That is nearly 300 gigabytes of memory saved just by dropping precision on the numbers.
And it boosts their single request decode speed by 55%.
That is heaps faster.
It is, but they go even further. For Kimi K2.6, they are fundamentally changing how they store the KV cache.
The key value cache, which is basically the model's short-term memory for a specific conversation, right?
Correct. It is what allows the model to remember what you asked it 3 prompts ago without having to, reprocess the entire chat history from scratch.
Right, right.
By storing that cache in 8-bit floating points instead of the standard 16-bit, they double the context capacity.
Double it.
Yeah. It goes from roughly 686,000 tokens up to 1.37 million tokens, and it cuts the cost per token by 30%.
Okay, hold on. Are they having a lend? I have to push back on this.
Go for it.
If you just blindly chop off decimal points and have the memory footprint, doesn't the AI just start hallucinating wild stuff?
You'd think so, yeah.
Like you're literally removing detail from its brain?
It is a totally valid concern, but you have to understand how neural networks actually make decisions. They are not doing exact, rigid accounting math. They are vast webs of probabilities. If you think of a model's knowledge like a topographic map, quantization isn't destroying the mountains and valleys.
Right.
It is just removing the millimeter-level elevation data.
Oh, I see.
The model still knows which way is down. So you generally only lose about 5 to 10% in strict accuracy on complex reasoning.
But you gain a model that is massively smaller and twice as fast.
Exactly. You keep the overall shape of the logic.
That makes heaps of sense. You don't need absolute mathematical perfection to guess the next word in a Python script. You just need the general direction of the weight.
Precisely.
But compressing memory like that, especially shared memory on a platform like Cloudflare, it has to open up some dodgy security holes.
Oh, it does, which is why they have to implement strict safety mechanisms alongside the speed hacks.
Right, you can't just run it unprotected.
No. Cloudflare added a layer of KV cache integrity checking. When you compress all that context into a smaller footprint, you risk memory collisions.
Okay, so data bleeding over.
Yeah. The integrity check ensures that your prompt doesn't accidentally read data belonging to another user's compressed memory space on the same server.
That would be disaster.
Total disaster. And the brilliance of it is the mechanism itself, they optimize the integrity check so heavily that it adds less than 1% of overhead to the total throughput
Less than 1%.
and practically nothing to the tail latency.
So they secure the compressed data without surrendering the speed gains.
Exactly.
And this obsession with brutal speed, it isn't just happening in the massive cloud centers, it's trickling all the way down to local hardware too.
Yeah, we are seeing it everywhere.
I was testing out an open source project called Dwarf Star, and it perfectly captures this vibe.
Oh, Dwarf Star is fascinating engineering.
It really is. It's a native inference engine, but it is built specifically and exclusively for running DeepSeek V4 Flash and PRO locally.
With a little bit of support for GLM 5.2.
Right. But it's not trying to be a general runner for every model format under the sun. It just does this one specific thing.
Yeah, it includes everything from model loading and prompt rendering to tool calls and an HTTP server, plus a coding agent built right into the engine.
And it handles scale in a really clever way. Like if you have a model that's too big for a single machine's RAM.
Yeah, Dwarf Star can split the execution across multiple machines using pipeline or tensor parallelism.
But instead of relying on massive enterprise networking gear,
It connects those machines over standard Thunderbolt cables.
or just basic TCP,
Yeah. It supports Apple's Metal backend on a Mac, as well as CDA and ROCm for PC hardware.
here is the analogy that helped it click for me.
Let's hear it.
Using Dwarf Star is like pulling the heavy leather seats, the touchscreen radio, and the air conditioning out of a standard street car to make it a dedicated track racer.
Oh, that's a great way to put it.
Right. You lose all the luxury and the universal compatibility, but you absolutely win on raw, stripped-down speed. You get a machine that does exactly one thing blisteringly fast.
That is spot on. You are trading versatility for pure velocity. And here is where this gets really interesting. This ruthless obsession with stripping away smart features for raw speed. It isn't contained to AI.
No, it's spreading.
Traditional software engineering is getting infected by the exact same philosophy.
Which leads us to GitHub. I was reading up on their recent overhaul of the code search engine, specifically how they handle case folding.
Yeah, this was a massive undertaking.
For those who aren't in the weeds on search infrastructure, case folding is basically how a search engine knows that a capital A and a lowercase a are the same letter when you're searching through millions of lines of code.
Yeah, it sounds incredibly simple, right?
You would think so.
But at GitHub scale, doing that character by character across billions of files is a massive computational drag.
Just a huge bottleneck.
Previously, their case folding process ran at about 3 gigabytes per second.
Okay.
They managed to accelerate that to over 45 gigabytes per second.
That is a 15 times speed multiplier. How do you even squeeze that out of a basic text search? You can't just throw more servers at it to get a single operation to run 15 times faster.
You have to change how the CPU actually reads the data.
Huh.
They achieve this by removing what developers call an early exit branch.
Okay, what does that mean in practice?
The traditional, supposedly smart way to write search code is to check the text. And the moment you find a matching sequence or a definitive failure, you stop checking and exit the process early to save time.
Right, why keep reading the sentence if you already know the answer is no?
Exactly, but that's a problem because of how modern processor pipelines work.
Oh, because of branch prediction.
Yes. A CPU is like a high-speed factory assembly line. It likes to guess what the next instruction will be and queue it up.
Okay.
When you put a conditional branch in the code, and if this, then stop decision, the CPU has to guess the outcome.
And if it guesses wrong,
It has to hit the brakes, dump everything on the assembly line, and start over.
which kills your speed.
It causes the pipeline to stall entirely. GitHub replaced that branchy logic with a branch-free byte arithmetic approach.
So they stopped trying to be smart about exiting early.
Exactly. They used a compact Unicode lookup structure and an allocation-free ASCII path. By removing the branches, they allowed the LLVM compiler to fully vectorize the operations.
Meaning it does things in parallel.
Yeah, it uses a CPU feature called SIMMD, single instruction, multiple data.
Right, I've heard of that.
Instead of reading one letter at a time and asking, is it a match, the CPU applies the exact same operation to 16 or 32 bytes simultaneously. No questions asked.
So the processor never has to guess, and it never pauses. It just blazes through massive chunks of memory like a bulldozer.
Exact.
But that is completely counterintuitive.
It really is.
Doing 2 full clean passes over an entire chunk of data is actually 15 times faster than a single pass that tries to be efficient by stopping early.
Yeah, it goes against the logic of basic computer science, where you are taught to exit a loop as soon as you can.
It highlights the physical reality of memory bandwidth and CPU architecture.
Branch prediction is just slower than raw, unthinking mathematics.
Yeah.
And the Rust programming language just adopted a very similar philosophy with their version 1.98 release.
I saw this.
They added algebraic floating point operations.
The fast math compiler stuff. Historically, compiler optimizations for floating point math are incredibly tricky, right? Because floating point addition in a computer isn't perfectly associative.
No, it's not.
Like in pure math on a chalkboard, A plus B plus C is exactly the same as A plus B plus C. But in a CPU, microscopic rounding errors mean those two operations might give very slightly different results.
Precisely. Because of those tiny discrepancies, the compiler usually refuses to reorder the math.
It plays it safe.
It forces the CPU to calculate everything in exact sequential order just to be safe, which is incredibly slow. But Rust 1.98 gives developers an explicit API to permit reassociation and fused instructions.
You are basically telling the compiler, I give you permission to shuffle these independent calculations around however you want.
Yes. By explicitly giving up a tiny microscopic bit of mathematical precision, you unlock that exact same SIMMD vectorization we just talked about with GitHub.
Wow.
The compiler can bundle the math operations together, significantly accelerating numerical workloads.
Again, we are trading microscopic precision or intelligence for absolute brutal speed.
His speed is winning every time.
And because the models are blisteringly fast and the code execution is fast, we are seeing the direct consequence of this. AI agents are now being unleashed into our systems.
Oh yeah, they're everywhere.
They aren't just writing chat responses anymore. They are actively writing code, deploying changes, and debugging systems in real time. But that opens up a massive can of worms.
It's a huge one.
If we have independent bots running around our infrastructure at memory speed, how do we actually secure them?
That is the million-dollar question.
If you reckon this stuff is as fascinating as we do, make sure to hit subscribe so you don't miss the next one.
The security aspect is definitely the next great frontier. And we are finally seeing enterprise-grade solutions emerge to handle these agents.
Like what?
Uber, for example, just open-sourced a system called ADR.
Which stands for Agentic AI Detection and Response, right?
Correct. It is an entire security apparatus built specifically to protect AI agents in a production environment.
What I find really interesting about Uber's approach is that they're focusing heavily on internal tools, too.
Yeah.
It's not just about stopping external hackers from manipulating a customer support bot.
Internal tools are arguably the bigger risk here. ADR covers employee-facing tools like Cursor, Claude Code, and Codex.
Think about the permissions an internal coding agent needs to function.
This is terrifying.
It has API keys, it can read your proprietary repositories, it can modify files on a local machine, and execute deployment scripts.
Yeah, if that agent gets tricked by malicious code buried in a third-party library, it can do massive damage.
So how does ADR actually stop a bot that moves that fast? You can't have a human review every API call.
You really can't. ADR works across 4 automated pillars: observing agent activity, evaluating the defenses, detecting threats, and actively blocking unsafe actions.
So it sits right at the execution level.
Exactly. When the agent attempts to run a script or make a system call, ADR intercepts the intent.
Okay.
It evaluates the context of the action against known safe patterns, and if it detects something dodgy, like an agent suddenly trying to dump a database instead of writing a unit test, it blocks the action before the agent can execute it.
That's brilliant.
Uber even had the accompanying research paper accepted at MLSCs, and they released the core components under an Apache 2.0 license.
So we are building automated guardrails to police the automated agents.
We have to.
And on the flip side of that, Cloudflare is building tools to help the agents see what they're actually doing.
Yes, Cloudflare is catering heavily to this new automated workforce. They just updated their workers platform to automatically capture open telemetry traces locally.
Oh, really?
Yeah, whenever developers or agents run standard commands like Wrangler Dev or Vite Dev.
Which means all the telemetry and error logging is generated right there on the local machine instantly.
And here's the clever part. When the Cloudflare tooling detects an active coding agent session, it directs the agent to a new Local Explorer API.
Okay, what does that do?
This is a local debugging interface where the AI agent can directly query its own traces.
No way.
Yeah, it can inspect its bindings and examine the state of the system across Cloudflare's databases like D1, KV, and R2.
That is a fundamental shift. The agent gets to debug itself.
Exactly.
Think about the old workflow. Copilot writes some code, you run it, it throws an error. You have to copy the error log, paste it back into the chat window, and ask the AI what went wrong.
It was so clunky.
With the Local Explorer API, the agent writes the code, hits an error, queries the trace logs directly, and fixes its own mistake without a human ever having to copy-paste a thing.
It creates a closed loop of iteration. The bot can fail and correct itself at machine speed. And to support these far more complex, agent-driven workloads, Cloudflare also just added inbound TCP connections and gRPC support to their Workers platform.
So agents aren't just building simple, stateless web endpoints anymore.
No, they are orchestrating complex, persistent microservices.
It's a bit wild to think about. While the agents are getting all this flashy new security and self-debugging capability, the underlying infrastructure, the actual server rails, is quietly having to mature to handle the sheer volume of traffic these bots generate.
Yeah, we have to scale the tracks to handle the trains.
Which requires much smarter scaling metrics.
It does. A great example of this evolution is how engineering teams are using Kita.
The Kubernetes event-driven auto-scaling tool.
That's the one. They're using it in conjunction with Amazon SQS. Instead of scaling up their Kubernetes pods based on traditional hardware metrics like CPU or memory usage, they're scaling based purely on queue depth.
Right, because if an AI agent suddenly dumps 1,000 complex tasks into a processing queue simultaneously, waiting for the CPU to spike means you are already too late to handle the load gracefully.
Exactly. In a queue-driven system, the number of messages waiting to be processed is a far more accurate and immediate signal of demand than server utilization.
That makes sense.
Kita uses a very elegant calculation. It takes the number of outstanding messages in the queue and divides it by a configured per pod target.
Okay.
If the math says you need 50 pods to clear the queue, it spins them up instantly.
And if it's empty?
If the queues are empty, it scales the entire deployment all the way down to 0, saving you money.
That makes heaps more sense. CPU is a lagging indicator.
It really is.
Scaling your servers by CPU usage is like sweating behind the espresso machine and suddenly realizing you are slammed because you can't keep up.
Right.
Scaling by queue depth is looking at the line, stretching out the coffee shop door, and calling in another barista before you even pull the first shot.
That is a perfect analogy.
Yeah.
It is predictive scaling rather than reactive scaling.
Yeah.
And alongside this smarter provisioning, the infrastructure is enforcing stricter safety rules by default.
Like what?
Well, look at the upcoming Kubernetes version 1.37. They are moving the user namespace feature, which is often called rootless mode, to beta.
Okay.
This allows node components to run without host-level root privileges, completely isolating them. They're also continuing the phase-out of the older SKI Group v1 standard.
It forces a cleaner, more secure environment from the ground up.
Exactly.
I saw Terraform is doing something similar with their Azure RM Provider 5.0 release. They are enforcing what they call opt-in pre-flight validation.
Which is a polite corporate way of saying they're making developers actually review and validate their configurations before they upgrade them.
Right, no more flying blind.
It simplifies the provider behavior and gives much better infrastructure feedback.
Yeah.
But the core theme across all of this is strictness. The tools are no longer letting you wing it. You cannot have automated AI agents running at machine speed on sloppy infrastructure.
You need absolute rigid tracks for the fast trains.
Exactly.
And if we step back and look at the whole board, we have AI models being quantized into smaller, faster footprints.
Yeah.
We have traditional text search code literally dropping its own safety checks just to process bytes faster via SMD.
Oh, yeah.
We have agents debugging themselves via local APIs and Kubernetes scaling based on predictive queues rather than lagging hardware stress. It is all pointing in one very specific direction.
It is the full industrialization of code generation. The craft of writing software is becoming a manufacturing pipeline.
And the ultimate proof that this speed and agent-driven infrastructure is winning comes directly from Microsoft. I was reading up on their CPP organization, and it blew my mind.
It's a massive shift.
They recently executed a massive internal shift. They migrated over 1,600 repositories and 3,100 developers away from their own Azure DevOps platform, moving them entirely over to GitHub.
Microsoft moving its own engineering teams off its own flagship DevOps platform is a massive admission.
It really is.
They kept Azure boards and pipelines through a hybrid integration purely for the project management side, but the code itself had to move to GitHub.
And the reason was entirely to access the Copilot coding agent capabilities.
Purely for the agents.
They ripped thousands of developers across environments in 6 months, specifically because they realized that if you don't have GitHub's agentic speed, you are dead in the water.
Even if you are Microsoft building the infrastructure yourself.
Exactly. The giants are entirely rebuilding their daily workflows around this automated velocity.
It is the new reality.
It turns out the future of coding isn't about teaching the machines to be flawless, it's about building the track fast enough for them to run on. Which leaves you with a slightly terrifying question. If AI agents are writing and debugging the code at memory speed, and the infrastructure is automatically scaling to handle it without us, what happens to the junior developer's learning curve? How do humans actually learn the physical craft of coding 10 years from now when the machines do the heavy lifting instantaneously? Something to chew on for your next stand-up. Vocal technologists, see you soon.
Spoken Tech for your ears.